Welcome back, guys. In two of previous videos, we learned about return to scale, and also we worked some general example about return to scale, especially using Cobb-Douglas production function. In this video, let's solve some numerical example about return to scale in order to clearly understand the concepts of returns to scale. So we have given three different types of Cobb-Douglas production function. The first one, y is equal to L to the power of 0.3 k to the power of 0.7. Second one, y is equal to L to the power of 0.5 k to the power of 0.6. And the third one, y is equal to L to the power of 0.4 and k to the power of 0.5. Let's assume that we are going to scale up each of these Cobb-Douglas type production function by a scale of t equal to 2, and assume that our initial output level is equal to 100. So if we scale up all input bundles in this Cobb-Douglas production function, and this one, by a scale of equal to 2, how much our output level will increase? It means that we are going to find out that by scaling up by equal to 2, either we are going to have a constant return to scale, increasing return to scale, or decreasing return to scale. So let's start solving the examples. So let's start from the first one. If we scale up each input by amount of 2, so then y of 2, y after scaling by 2 is equal to 2L to the power of 0.3 multiplied by 2K to the power of 0.7. We are going to scale up each input by some multiplier of equal to 2. Then we will have here 2 to the power of 0.3, L to the power of 0.3, 2 to the power of 0.7, and k to the power of 0.7. We have 2 to the power of 0.3 and we have 2 to the power of 0.7. So then it will be equal to 2 to the power of 0.7 plus 0.3 will be equal to 1. Then multiplied by L to the power of 0.3, k to the power of 0.7. And we know that L to the power of 0.3, k to the power of 0.7 is equal to this initial production function, which is equal to y. Then it will become equal to 2y. And what we have, initial output level is equal to 100. Then 2 multiplied by 100 will be equal to 200. So now, when we scale all inputs by some amount of equal to 2, our output level increased from 100 to 200. That means we doubled our input, then our output also doubled. Because when we divide 200 by 100, 200 divided by 100 will be equal to 2. It means this 2. Our output level increased by 2. It's also doubled. So we know that if y of t is equal to t of y, then we will have what? We will have constant return to scale, which in this case exactly what we have, which is equal to y of 2 is exactly equal to 2y, because now t is equal to 2. So in the case of first Cobb-Douglas production function, what we have? We have constant return to scale. Constant return to scale, because our output level increased exactly by the same amount that we scaled up all inputs within this Cobb-Douglas production function. So now let's move to the second one. The second one, again, y of 2, that means output level after scaling up all input by amount of 2, then we will have 2L to the power of 0.5, 2K to the power of 0.6. Then we will have 2 to the power of 0.5 multiplied by L to the power of 0.5, 2 to the power of 0.6 multiplied by K to the power of 0.6. Then we will have here 2 to the power of 0.5, 2 to the power of 0.6. We will have 2 to the power of 1.1 multiplied by L to the power of 0.5 multiplied by K to the power of 0.6. Again, L to the power of 0.5, K to the power of 0.6 is equal to this initial production function, which is equal to Y. Equal to Y. Then we will have here 2 to the power of 1.1 multiplied by Y. Then 2 to the power of 1.1, and instead of Y, let's put the initial value, which is 100, then this one, 2 to the power of 1.1 will become to 2.14. Then 2.14 multiplied by 100 will become 214. So in this case, when we increase all inputs, which is labor and capital, by a scalar of equal to 2, our output level increased from 100 to 214. Increased to 214. If we divide 214 to 100, so our output level increased by 2.14, although we increased input by 2. So then in this case, we talked about that in previous video. If you didn't watch yet, so I will put the link here somewhere around. Then you can watch those videos, how we will have this kind of like situation. We know that if y of t is greater than t multiplied by y, which is exactly in this case, y of t is equal to 214. And it's greater than t multiplied by y. T multiplied by y, which is equal to 2 multiplied by y, is 200. So in this case, 214 is greater than 200. So in this kind of situation, what we will have increasing return to scale. In this situation, we will have increasing return to scale, because our output level increased, but by more than what we scaled our input. We scaled our input by 2, but our output increased by 2.14, because when we divide 214 to 100, it's become 2.14. So then y of t is greater than t of y. That means 214 is greater than 200. This 200. So in this case, we will have increasing return to scale. So let's make this one clear as well. So in the case of third Cobb-Douglas production function, which is equal to y is equal to L to the power of 0.4, K to the power of 0.5, let's solve this one. Again, y of 2, y after scaling inputs by some amount of 2, we will have 2L, 2L to the power of 0.4 multiplied by 2K to the power of 0.5. Then let's make it like very, very short. 2 to the power of 0.4, 2 to the power of 0.5. We will have what? We will have 2 to the power of 0.9. Then L to the power of 0.4, K to the power of 0.5. And again, we know that L to the power of 0.4, K to the power of 0.5 is equal to this initial production function. So instead of this, we can only add Y. Then we can write down this one, 2 to the power of 0.9 multiplied by Y. And 2 to the power of 0.9 is equal to 1.18. Then we can write down 1.86 multiplied by Y. Our initial output level is 100. Then multiplied by 100. 1.86 multiplied by 100, it will become equal to 186. 186. So now we scaled up our input by amount of 2, but our output increased from 100 to 186. What does it mean? It means we doubled our input levels, which in this case labor and capital, but our output increased, but by less than double. Because if this one increased by double, so it should be 200, but now it's increased just by 186. So if we divide this one, 186 divided by 200, it will be 186. We scaled up input by 2, but our output increased by 1.86. So in this case, we have that if y of t, y after scaling, is less than t of multiplied by y, which is y of t is equal to 186, is less than t multiplied by y, which is 2 multiplied by y. Y is what? 100. 2 multiplied by 100 is equal to 200. So in this kind of case, which is output increased but less than the multiplier or scalar, so in this case, we will have decreasing return to scale. We scaled up by 2, but our output increased by 1.86. So here what we will have? We will have decreasing return to scale. So in this example, we worked on the concepts of return to scale based on 3 numerical Cobb-Douglas type production function, which each of them exhibit a different types of return to scale. The first one is an example of constant return to scale because output increased exactly by amount of scalar, which we scaled by 2, so output increased by 2. The second one, which is an example of or an illustration of increasing return to scale, which we scaled up our input by 2, but our output increased by 2.14. 2.14. That means more than that. And the third case, we have like illustration of decreasing return to scale because our output increased but less than what we scaled up our input level. So this is a numerical example and clear example about the concepts of increasing return to scale, constant return to scale, and decreasing return to scale. Still, if you have any questions about the concepts of return to scale and 3 types of return to scale, write down in the comment section below. I will try to answer your questions as much as possible, as clear as possible. And I request you to subscribe my YouTube channel, comment, like, and share with your friends in order to grow up. Thank you so much. See you next time.